This last talk will be very helpful. He will talk about the short fruits of rainbow mechanism.
Okay, so thank you very much. So if anything is not clear, please unmute yourself and ask me a question, because I would not be able to read the chat. Obviously, I would be looking on the board and on the screen. If for some reason suddenly the voice disappears or anything, please let me know. So I'm going to talk about joint work with David Munha Correia, who is an absolutely fantastic student we have in ETH, and Pokrovskiy, whom many of you know. And this would be about finding rainbow copies in H-color graph. So the basic problem is the following. You have an H-colored G, and you ask which rainbow copies of which graphs H you can find inside G as rainbow copies. And for me, always H coloring in this form would be either proper, which means at every vertex you have only one edge of specific color, or maybe bounded, which means at every vertex you might have, let's say, two edges of the same color, but not more, some small number. And H, the copy which I want to find, would be always a matching. So basically I would have H-colored graphs, and I would want to find in it a rainbow matching, right? We want this matching in rainbow, which means all edges get distinct colors. I hope the problem is clear. And the first instance of this problem goes back many years to the work of Euler, right? In 1700s, right? And so Euler was interested in the following object called Latin square, right? So Latin square you can obtain, let's say this would be a 4x4 Latin square. You have n by n square, and it's squares here filled by numbers, like here 1, 2, 3, 4, and then 2, 3, 4, 1, and then 3, 4, 1, 2, and maybe 4, 1, 2, 3. So you have n by n square. Every row and column contains all the numbers from 1 up to n, the permutation, and in such a way that every column and every row contain distinct numbers. So this is a Latin square. And what Euler was interested to find in this Latin square, so he had some specific problem in mind called transversal. So let me give you an example. So transversal is a collection of squares such that no two of these squares are in the same row, no of these squares are in the same column, and they also contain all distinct symbols. Like here is 2, 3, 1, and then 3, 1, 2. And then transversal would be, I take this 2, I take this 1, and I take this 3. Is this clear? And what, to say it in a graph theoretic language, what you can easily observe that a Latin square is nothing else as proper NH coloring of complete bipartite graph KNN. Indeed, every entrance of the Latin square, you can think about H. The entries, for example, this is row 2 and column 3. It's like an H connecting vertex 2 on the left with vertex 3 on the right. And 4 would be the color of this H. So therefore, Latin square, it's nothing else but proper NH coloring of the complete bipartite graph KNN. And transversal is just a rainbow perfect match. Actually, many times I would say transversal of size n-1. So my transversals would not necessarily be full. So they sometimes would be of smaller size. And therefore, when I say transversal of size something, it means it's a collection of that many squares, no two in the same row, no two in the same colors, containing different symbols. But it's much easier to think about, I would be talking about not perfect matching, but rainbow matching of some size. Right, so this is a setting, and the main conjecture, one of the main conjectures on this, in this topic, is this conjecture by Gualdi, Reiser, and Stein from 60s, which says that every properly NH color KNN has a rainbow matching size. It's easy to see that we not always can have a full rainbow matching. For example, if you take an addition table of the group of even order, right, let's say cyclic group Z2K, right, you will not have a as a coloring, you will not have a rainbow perfect matching, but the conjecture is that you always have a matching of size n minus 1. So this conjecture is still widely open. So it was extensively studied over the years. So let me not go and mention all the results, but let me mention two recent. So until very recently, the best result was in this area the fact that you can always find a matching of size n minus constant log square, and this was by Hatami and Shaw. Shaw first had some proof, we had some in 80s with some mistake, and then together with Hatami, they corrected it. And very recently, together with Kivash, Pokrovskiy, and Berger, we improved it to n minus a constant, roughly log n divided by log n. So it's Kivash, Pokrovskiy, Sudakov, and Berger, it's 2022. So these are the best known results. So the conjecture of Boaldi and Stein, Boaldi, Reiser, and Stein, generated a lot of activity, and in particular, there were several more strong conjectures which extended this one, and one of them, which I want to talk about, is the conjecture of Aharoni and Berger, which says the following. So every properly H color bipartite right? Who's right? So since each properly H colors, every color class is a matching. So with n colors of size n plus 1 has a rainbow matching size. So you take a bipartite graph, multigraph actually, it's not necessarily graph, it's also multigraph. I allow you to repeat edges. So you take basically n matchings, every matching is of size n plus 1, every matching is a color. You take the union in such a way that the resulting graph is bipartite. You can repeat the edges. So for example, you can have green copy of the edge and the blue copy of the edge, and then conjecture of Aharoni and Berger from I think 2009 says that in this graph you can find a full rainbow matching. So rainbow matching using all the colors. Now I said that this is a more general problem than conjecture of Boaldi, Reiser, and Stein, and indeed what you can do. So here is a short proof to show you that this is indeed a more general problem. You can do the following: you delete one color. Right? You really don't care, right? You take a problem about Latin squares, right? So you take a proper NH coloring of KNN. You delete one color, right, from KNN, right? And then observe what you have. So you can have the number of colors which is left is n prime, which is n minus 1. And every color has n edges, right? Color has n edges, which is n prime plus 1, right? Edges in a color. And therefore, if Aharoni-Berger conjecture was true, then you can just take, right, this coloring of KNN, delete one color, and apply to it Aharoni-Berger, to get a full rainbow matching of size n prime, which is n minus 1. And you would prove Aharoni-Berger. You would prove Bualdi-Reiser. So Aharoni-Berger is a more general conjecture. And people were interested to study this problem. Now, obviously, since I told you we don't know to prove Bualdi, Reiser, and Stein, this more general conjecture, we equally don't know to prove it. So therefore, the attempt was to obtain a result in the spirit of the result we have for Bualdi, Reiser, and Stein, which means not get a full rainbow matching, but get a rainbow matching of slightly smaller size. Actually, here it's more interesting because there are two kinds of approximate results which you can get. And I call them weak asymptotic and strong asymptotic. So what weak asymptotic would mean? The weak asymptotic means that you have bipartite multigraph, which is union n colors of size n plus 1, right? Exactly like that. And you get a rainbow matching of size n minus little of n. And you try to get this little of n better and better, hopefully in the end getting it to be 0. Right? This would be a weak asymptotic result for Aharoni-Berger. Now there is another thing which you can do, which we call strong asymptotic result. And strong asymptotic result, again, you start with a bipartite multigraph, which is union of n colors of size, but now you take your color slightly bigger, so every color will size n plus little of n. And your goal would be to prove that there is a rainbow matching of size n, right? So there is a real full rainbow matching containing all the colors, okay? Right, so this is a strong asymptotic. And these are two approximate versions of Aharoni-Berger conjecture. Now, obviously, because I gave them names strong and weak, you would expect that this is true, that strong implies weak, right? It's really a stronger statement. And the reason is the following, right? So the reason, so here again, the proof, right? So you start, right? And so I want to show you that I know this weak result if I know the strong result. You start with n colors of size n plus 1, and then you delete middle of n colors, exactly as before. Just completely arbitrarily throw away middle of n, right, middle of n colors. So now you have, right, we still have every color of size. Let's just look how many colors we have. We have n prime colors, which is n minus middle of n colors of size, but size of the color didn't change. It was n plus 1, which is now would be n prime plus middle of n prime, right? And so therefore you now can use strong asymptotic to get rainbow matching size and prime, right? So again, it's very easy reduction. So you indeed see that the strong asymptotic is stronger than the weak asymptotic. Any questions? Now, again, as name suggests, somehow weak asymptotic, right? We saw that, there is this reduction. Historically, it was easier to prove. So for weak asymptotic, right, theorem was known already for quite a number of years. It was proved by Berger, Grinblat, and Sarkozy, right? And it's a very short and elegant proof showing that bipartite multigraph with n colors of size n+1, exactly our setting, right? The edges are union of n colors. Every color is a matching of size n+1, right? I always talk about this setting, right? My color classes are always matching in this case, imply rainbow matching of size n minus square root of n, right? It's actually really very explicit good little of n, right? So it's a square root of n. So if you have an Aharoni Berger conjecture setting, you always have a matching of size n minus square root of n, which is rainbow. Right? And as I said, I mean, usually when I give a slightly longer talk, not 40 minutes, I show this proof, right? I could fit it in one word here. So you can believe me that this is a short proof using elegantly alternating past technique. Okay, so this is about weak asymptotic. On the other hand, strong asymptotic took much more effort to prove. Now observe that what we want in strong asymptotic, we start with n matching, but not of size n+1, but of size bigger than n+1. But our goal is to get full rainbow matching, the rainbow matching which uses all the colors. So what people need to prove? So first you observe that matchings of size 2n is enough by using greedy procedure. Right? If you have a bipartite graph such that every color class is of size 2n, and it's a union of n matching of size 2n, then just greedily you can build your rainbow matching of size n, just because every edge destroys you 2 edges of the other color. Now this trivial bound to n was improved to 7n/4 by Aharoni, Charbit, and Hall. Then it took some time and it was improved to 5n/3 by Kotler and Z. Then Losha Pokrovskiy proved the bound 1.618 n. So it's something, it's a golden ratio, essentially. Then again, what does it mean? It means if you start with n matching of that size, you find a rainbow matching. Then there was a result of 3n/2 by Clemens and Müller, and independently by Aharoni, Kotler, and Z. And finally, Pokrovskiy proved indeed the strong asymptotics, that the matching of size n plus little of n, n matchings are enough. One remark about this proof, that originally it was very difficult proof, right? It was many clever ideas. It was 40-page paper, and the little of n which Alexei gets is like barely superlinear. Okay. So why I'm telling you, right, this whole history, just to indeed indicate that historically somehow the belief was that the strong asymptotic is much harder to prove than weak asymptotic. And one of the main messages which I want you to take home from this talk is that actually this is not the case. So what I'm going to present you is something which we call sampling trick. And this sampling trick shows that in this conjecture and several others which I mentioned, the following is true, right? That if you have weak asymptotic result, this error term, where this little of n is something like n divided by f of n. Right? So in particular, for example, if you look on Barat Barat Garfash Sarkozy, so this f of n is square root n. Right? So weak asymptotic with error little of n implies, just very shortly, I will show you the derivation, strong asymptotics with error term n divided by square f of n. So that's kind of the main thing I will first show you how to do, and then I'll tell you a little bit more applications of this trick. Right? So in particular, is it clear? Right? So what we're going to prove, right away, using Barat Garfash Sarkozy, is that the following theorem, which gets much better error terms in the Pokrovskiy's result, right? Theorem Munha Correia itself. Bipartite multigraph with n colors of size n plus, so if you plug here square root of n, so this error term should be n to the 3/4, and let me put here 7n to the 3/4, implies rainbow matching size. And that's what I'm going to show you, and hopefully I will not do full computation because they're pretty standard, but I hopefully will fit this basically here in this block. Any questions, right? So the goal is to show that if I start with a bipartite multigraph whose edges are colored such that every color class is a matching of size slightly bigger than n, but n to the 3/4, I can find you a full rainbow match. And I will going to use the result of Barat, Garfash, and Sarkozy. So if every color class is just a matching of size n, then I can find matching of, rainbow matching of size n minus square root, right? And that's a known result. And as I said, it's not even difficult to prove. I could have do it on another board if I would have had time. So actually, let's see how I'm doing. Maybe I'll indicate something about this. So here's a proof, right? So given, right, n matchings, n colors, matchings of size n plus 7 n to the 3/4, we'll do the following. We construct a random set of vertices. So let S be a random set such that probability that any vertex X belongs to S equals P, which is twice n to the minus 4. What you do, you look on the your ground set and you pick every vertex with probability 2 to the minus n/4 and you put it inside S. And let's do the following simple observations. First of all, for any color C, right? Let's look how many edges of color C fall inside S. So I claim that S contains very close to p square n, right? Because if you take an edge, probability that you choose both of its endpoints is p square. And because every color class is a matching, they are disjoint, these are independent events. So you expect p square n edges of this color, which is, for me, the only thing which would be enough that it's bigger than 2 square root n. And it's very easy to see, right? The size of the color is more than n. This is 4 times square root, 4 divided by square root n. So this is easy. And again, this thing would be concentrated. So I really would get that many edges with very high probability, right? So this is a standard Chernoff. I will not do the computation. Now, also, for every color C, if you look on the complement of S, right, G minus S, how many edges of this color it loses, right? So G had that many edges of every color. How many edges of the color you lose? In order to lose an edge, it should contain at least one vertex from S, because you're putting S aside. The probability of this is P. Since H has 2 endpoints, the probability that one of them is in S is at most 2p, right? Or it's precisely 2p actually, right? Because these are independent. At most, right, it would be is at most 2p, right? Because you can have both or only one of them. So we expect 2p times n such edges, which is again 4 times n to the 3/4. Right? So again, and again, what is sure is that for disjoint edges, it's again independent event. So probability for one edge is at most 2p, right? To have at least one vertex, because sometimes it can be both. And these edges I put aside. So I will lose at most that many edges when I look on G minus S. Okay. So in particular, every color has more than n edges in G minus S, right? So now we in perfect situation, right? So we can apply Chernoff bound and deduce that with high probability, we have the situation that we put aside set S, inside G minus F, every color has at least n edges, actually strictly more, right? Say bigger or equal than n plus 1. And therefore, I can now use Berger, Grinblat, and Sarkozy. By Berger, Grinblat, and Sarkozy, G minus S has a matching rainbow matching, right? Size n minus square root of n. So I already have a matching of size n minus root of n living in G minus S, right? And so let C1, C2 up to C square root n missing colors. Now it's absolutely clear what you will do, right? You have put aside a set S, right, which contains all the colors. Moreover, every color appears inside S at least 2 square root n times. There are 2 square root n matchings of this color in S, right? So what I will do greedily choose S rainbow matching in colors C1 up to C square root n, right? And what you need to know, right? Choosing S rainbow matching, let's call it M. Right? Know that after using high edges in N, we destroy because matching of size S has matching of size I has two ion points. Every color class is a matching, so you destroy at most two I edges. Since the total number of edges of every color is typically more than 2 square root n, I can do this greedily. I just choose edge of color 1, throw everything which touches this, edge of color C2, and so on. So I got this matching M together with this rainbow matching of size n minus square root n, gives me a rainbow matching and shows, right, the main claim which I wanted to make, that in this particular problem, the weak asymptotic is actually as strong as a strong asymptotic, right? You can deduce the whole proof, right? This together, if I would have shown you Barat, Garfash, and Sarkozy, it would be one page. So this is a good,
something.
yes, good place to stop and.
Yeah, I just want to make sure I understood correctly. So you said that G delete S has 2 PM edges, but probably what you meant is like number of edges meeting S is about 2 PM, right?
I mean, this is what I call losing, right? So these are the edges which are not completely contained in GS, right? Right, for every color C, GS loses, oh, sorry, I didn't write it, I said, but loses at most
I see, okay.
that many edges.
Uh-huh.
Right, absolutely, sorry, very good, good remark, right? I said it, but I didn't write. So these are the number of edges of color C, which are not completely contained here.
Right.
And therefore, since the original matching had surplus of 7 n to the 3/4, and I lost only 4, right? I need to put a little bit more because by Chernoff, right, I would be concentrated around expectation, but not precisely equals expectation. I still would have at least n plus 1 edges left, which is precisely what I need to apply Barat, Garfash, and Sarkozy. Is this clear?
Yes, thank you.
Yes. Okay, so this is a sampling trick, right? It's extremely simple and therefore quite versatile. And I want to mention several other results which we managed to prove using this observation. They obviously would be a little bit more involved than this one, and that's why I choose to show you, because this is probably the cleanest and the simplest application of this trick. Any questions? Okay, so now let's go further. So observe that Aharoni, Berger talk about bipartite graph, but actually there is a non-bipartite version of Aharoni, Berger, right? So this was a conjecture which was made by Gao, Ramadurai, Vadles, and Vormal, right? And they conjectured that if G is a multigraph, which is a union of n colors, right? Again, it's a proper coloring of size. And now, because you're not bipartite, you need to have matchings of slightly bigger size, but the conjecture is only extra 1 is enough. So if you have n colored matchings of size n plus 2, now you don't assume that the union is bipartite, then they conjecture that G has a rainbow. So this was conjecture, and until recently it was quite widely open, and you can imagine why. Because when we're working with bipartite Aharoni Berger, we have this powerful false theorem. We have also the kind of very useful proof using alternating paths, and it doesn't work quite well for non-bipartite graph. So the only result which we're aware of is that the result by Aharoni, Berger, Chudnovsky, and Zerbik. And what they proved that there exists a rainbow matching of size at least 2 certain. So they showed that the conditions of the problem apply the existence of rainbow matching of size 2 certain. And so the next theorem which we proved is we got a strong asymptotic version of non-bipartite Aharoni Berger conjecture, which says that n colors of size n plus say 20 n to the power 1 minus 1 over 16. Right? So I just writing you the error term. It's still kind of, we have polynomial gain, implies rainbow matching of size. Right. So if you have matchings of slightly bigger size, you get a rainbow matching of size. And again, how we proved it? We first proved a weaker version, so-called weak asymptotic of this problem. We showed that if you have n matching of size n plus 2, then you're getting a rainbow matching of size n minus n to the power 7/8, right? And then, as I said, you will do this random sampling trick, which is pretty straightforward. Actually, the difficulty here, now we know to prove the weak asymptotic result, right? So we prove weak asymptotic result with error term n to the power 7/8, and then the sampling trick, very much as I described, you can just repeat this proof, will give you this result with error term n to the power 1 minus 1 over 16, which is like n divided by square root of the previous end. Okay, any questions? Very good. So let me mention another problem. I actually have another 2 problems, but we'll see how I manage. Right, let me mention another one, maybe which is slightly different. And it's slightly different because in this problem, my coloring is not a proper coloring, but what I said is a bounded color. Because at every vertex now I will have 2 edges of the same color. And this is a conjecture of Alspach, right? Conjecture by Alspach, and it's pretty old conjecture from, I think, 88. And so Alspach conjectured the following. So suppose you have G, which is 2D regular graph. Which union of D colors, every color is a 2-factor. Is it clear? So you take some number of vertices. On this vector, you take a 2-factor, which is a spanning union of cycles. Every such 2-factor gets its own color. You have total D, the HD join, so you get 2D regular graph. So if this is your situation, then Alspach conjecture, then G has a rainbow image. So he conjectured that you can have a rainbow matching which uses all the colors. Okay, so this is a conjecture of Alspach. And again, right, there is a weak version of this conjecture, which you can imagine, which was proved weak asymptotic, which was proved by Anstey and Pacheta, which says that in this situation, G has a rainbow matching of size D minus D to the power 2 thirds. So actually pretty good error term. So it's a polynomial some power of D less than 1. Right? So this is a weak asymptotic. So this was known, and on the other hand, the strong asymptotic was not known. Right? So this is again one need to say what one means by strong asymptotics. So the strong asymptotics here would be the following result. So you look on this 2D regular graph, and this 2D regular graph obviously should have at least 2D plus 1 vertices, right? And what you can ask, suppose I look on 2D regular graph, which is a union of D factors, right? Every factor has its own color, but the number of vertices is bigger than 2D. can I then find a rainbow matching of size D? Okay, so that would be a strong asymptotic in this case, right? And that's what people looked at, right? So and there are a bunch of the results which I will mention to you, right? So the first result that if G has at least 4D minus 3 vertices, then greedy works. And again, in strong asymptotics, I really want a full D matching, right? I want a matching using all the colors. So if your graph has twice as many vertices as the minimum it can have, then you can just build your matching greedy. And then already to get slightly less than that requires some proof, right? So 4D minus 5 vertices was proved by Alspach, Heinrich, and Lee. So that's already was some proof. Then this 4D was improved, the already constant was improved to 3.32 D vertices. And this was by Kuider and Sudakov. Then it was further improved by to 3D minus 2 vertices. So there was one more improvement to roughly 2 square root 2D vertices, right, by Ku, Wang, and Yao. So, and again, it's a kind of a similar story, right? That, you know, the weak asymptotic, you kind of get relatively easily because of variant of alternating paths and things like that. And on the other hand, the strong thing somehow seems harder. And again, if you use the sampling trick, here it's a kind of a bit more involved proof, but not much, right? Maybe 1 page. I will not show it to you, but the theorem which you can prove is that if G is 2D regular on 2D plus, say, D to the best we can get 3/4 plus epsilon vertices, union of D D2 factors, union of D colors, each color is 2 factor, then E has a rainbow, full rainbow matching. So we have a rainbow D match. And actually, right, for people who know, you can easily observe that if you wanted, let's say, a weak asymptotic result or result of this sort, then you can reduce this problem somehow to this famous Rodel-Nibel type results, which talk about matchings in regular bounded codegree hypergraphs. So this is indeed kind of can be obtained very classically, and what was missing was this sampling tree. So there is one more result which called Grinblat problem, but I don't think I have time for that. But you're most welcome to look on the paper, it's all there, and let me stop here. Questions?
Question?
So this Alspach's conjecture, you didn't write that the graph has exactly 2D vertices, but that's what's assumed, right?
The graph has at least 2D plus 1 vertices, that I said, right? It cannot be less, right? Because it's too far, right? Right. So obviously, right? So let's write it down. Obviously.
I see. So
it's at least 2D plus 1, right? And so the strong asymptotics, you're trying to get as close to 2D as possible, and it gets more difficult, right? If you tell me that you have twice as many, right, that would be very easy. right? You can just do greedily, but if you want a little bit less, you already need to work, right? And the goal would be to get at least asymptotically to D. That's what we can get. Obviously, I mean, it would be great to get precisely to D plus 1, right? But that's not what we can do currently, right? The sampling trick, it's really, right, exactly the message I told you, right? It just shows you that many times when you prove a weak asymptotic result, and many times it's not very difficult, or you know because you have tools, and you say, okay, but I want now to get a strong asymptotic. So our message is that you can many times get it more or less immediately by this sampling trick.
So the theorem is the graph has at least that many vertices, then you're
Right. The theorem is on at least that many vertices. Obviously, if it has more, then better. Right. So again, the G2 regular graph on at least that many vertices, which is union of D2 factors, which are colors, has a rainbow image. Right. And this is 3/4 plus little of 1. And because of, right, we proved first the kind of weak version using some variant of nibble, right? We're just quoting it. Again, it's not a very long proof because you can quote things off the shelf and then just apply the sampling trick properly, and that's how we get it. Right, and for people who remember nibble, though, they probably remember that there is this result that if you have a regular hypergraph where all co-degrees are bounded by constant, because that's what would be the case here, then you have error term, right? You have nearly perfect matching with error term roughly square root of right, n divided by square root of the degree, right? Your n is here d, so square root of n, d divided by square root of d, you get error term square root. And because we're applying sampling trick, our square root becomes 3/4.
Any other concerns? If not, let's take the speaker again.
Thank you.